Hello, everyone. Okay, so last time we've reviewed some basic algebras which are required for this class later on. And especially, we will focus on the Gauss-Jordan method, right? And which uses three types of elementary row operations, which are row multiplication, row addition, and the change of each rows. Okay, and we've reviewed some other basic concepts such as basic and non-basic variables, and linearly dependent and linearly independent, things like that, right? So when you consider a set of vectors, if one vector can be expressed by a linear combination of other vectors, then we could say those vectors are linearly dependent, right? And we've also talked about rank of matrix, which means the largest number of linearly independent vectors, and the inverse of a matrix. So we've learned if we know the inverse of vectors, then we could find the unique solution for a scalar linear system, right? And today we are going to talk about basics of linear programming modeling and some important assumptions of linear programming, as well as some formulating technique of LP problems with various example problems. And just to let you know, any LP, any linear programming problem with only two variables can be solved graphically. So if time allows, you will learn it from today's lecture, okay? So does anybody knows who this is? He's the biggest guy, I could say, at least in the linear programming area. Okay, his name is George Dantzig, who is called the father of linear programming. Okay, and he's the inventor of simplex method for solving linear programs. Of course, we're going to learn it sometime later in this class. Okay, then the linear programming uses mathematical models to describe the problem of concern, right? And here, the linear means that all the mathematical functions, the models are required to be linear functions, right? The programming does not refer to the computer programming here, but it means the planning. So the linear programming means the planning of activities to obtain the best solution or the optimal solutions. And the linear programming problems and their models are referred to the LP, or linear programs, okay? And a remarkably efficient solution procedure, which is called simplex method, is available for solving even the realistically sized linear programming problems, okay? And like it says, because of many real-world size problems can be modeled as LP, we use linear programming models, okay? Also, many other problems can be approximated as linear programs. So LP solution techniques provides the foundation for solving for many other structures of mathematical programs, okay? So before formally defining a linear programming problem, we define the concepts of a linear program, define the concepts of linear function and linear inequality, okay? The linear function has the general form just like this. So the linear functions are very simple, right? Here are some examples of nonlinear functions. So as you can see, these nonlinear functions are much more complex than the linear functions. Okay? The function fx is a linear function for a set of constants if this relationship is satisfied. So for example, f x1, x2 equals 2x1 plus x2 is a linear function of x1 and x2, right? However, this function f x1, x2 equals 2 times x1 squared plus x2 is not a linear function of x1 and x2. And for any linear function fx and any number b, the inequalities fx is less than equals b or fx is greater than equals b are called linear inequalities. So for example, these are linear inequalities. However, this is not a linear inequality. Okay? And last time I said the optimization problem is a computational problem whose objective is to find the best of all the possible solutions, right? And LP is a special type of optimization problem in which both objective function and the constraints are all linear functions, right? So formally, LP can be defined as follows. The LP, the linear programming problem, is an optimization problem for which we do the following things. We attempt to maximize or minimize a linear function of the decision variables. And the function that is to be maximized or minimized is called the objective function. The values of the decision variables must satisfy a set of constraints. So each constraint must be a linear equation or a linear inequality. That is, any linear constraints has the following general format. Okay? So for example, all of these math formulations are linear constraints, right? The sign restrictions, either non-negative, that is, left-hand side is greater than, equals 0, or non-positive, that is, the left-hand side is less than equal to 0, or the unrestricted in sign may be associated with each decision variables. And when you write a problem as a linear program, we are making a few assumptions about the underlying process. They are proportionality, additivity, and divisibility, and certainty. Okay? So the proportionality assumption is that the contribution of each decision variable to the objective function or constraint function is proportional to the value of that variable. So for example, doubling or tripling a decision variable will double or triple the contribution to the profit function or the cost function. And the additivity assumption of linear programming is that the contribution of any variable to the objective or a constraint function is independent of the values of the other decision variables. Okay? What about the certainty assumption? Certainty assumption of linear programming is that each parameters, which includes the cost coefficient in the objective function, and right-hand side of each constraints, and so on. Each of these parameters is known with certainty, which means all the parameters are not random. So actually, this assumption is almost never satisfied in the real world. right? So that's why the sensitivity analysis can help to find out the robustness of our optimal solution to certainty of data, okay? And finally, the divisibility, or someone says is continuity assumption of linear programming, is that each decision variable is allowed to assume fractional values, which means the real values, right? That is, each decision variables are not restricted to a discrete set of values, that is integers, okay? Okay, then let's take a simple example, okay? Winder makes two different products, doors and windows, in 3 different plants, okay? The batch of doors requires 1 hour at plant number 1 plus 3 hours at plant number 3. And a batch of windows requires 2 hours at plant number 2 plus 2 hours at plant number 3. And we assume that plant number 1 is available for 4 hours per week, plant number 2 for 12 hours per week, and plant number 3 for 18 hours per week. And also we assume that the profit per door batch is $3,000, and the profit per window batch is $5,000. Then we'd like to know that what should Winder manufacture to maximize profits. And this table summarizes the given data sets, okay? So to formulate the mathematical linear programming model for this problem, first of all, we begin by defining the relevant decision variables, right? What is the decision variable? I said it's a number of variables whose values are to be determined within the model, right? So in any linear programming model, the decision variable should completely describe the decisions to be made, right? So in this case, clearly the decision maker in this window company must decide how many doors and windows should be produced each week. Is that right? So we define 2 decision variables, let's say x1 and x2, okay, which represents the number of batches of product number 1. That is the, let's say, door produced per week. And x of 2, x2 represents the number of batches of windows produced per week. Then once we define the decision variable, we've learned that the next step is to determine our objective function, right? For this problem, what is our goal?
Maximize profit.
Yes, maximize profit. Thank you. But sometimes we might have minimized the cost, things like that, okay? But in this case, definitely our goal is to maximize the profit, right? So if we let G is the total profit per week, of course in thousands of dollars from producing these 2 products, then our objective function would be look like this, right? Maximize $3,000 times x1 plus $5,000 times x2. And let's set this objective function is equal to z, okay? Now we need to determine if the values of each decision variables are limited by any restrictions, right? So according to the problem description, each batch of doors produced per week uses 1 hour of production time per week in plant number 1, right? Whereas only 4 hours per week available right? So this restriction is expressed mathematically by the inequality x1 is less than equals 4. So we have x1 is less than equals 4 as a constraint, right? Likewise, plant number 2 imposes the restriction that 2x2 is less than equal to 12, right? And for plant number 3, you'd get 3x1 plus 2x2 is less than equals 18. And finally, because the production rate cannot be negative, so it's necessary to restrict each decision variable, x1, x2, to be non-negative. So eventually, you'd get the complete LP model for this problem like this, okay? Which includes objective function and constraint sets, including the non-negativity restrictions. Then let's consider another example. We'd like to make tables and chairs to maximize profit. Okay? And the profits are expected $16 for each table and $10 for each chair. And each table uses 2 large bricks and 2 small bricks. Okay? And each chair uses 1 large bricks and two small bricks. Okay? And you are limited by the availability of materials. So you only have 6 large bricks and 8 small bricks. Okay? Then the question is, to maximize your profit, how many tables and chairs should you make? Okay? So again, as always, we begin by determining the decision variables, right? The decisions that must be made by the decision maker would be the number of tables produced and the number of chairs produced, right? So we define 2 decision variables. Let's say T is the number of tables produced, and let's say C is the number of chairs produced. Okay? And we'd like to make the tables and chairs to maximize profit. So again, our objective function would be maximize the profit. Okay? And in our case, profits are expected $16 for each table, right? And $10 for each chair. So our objective function would be maximize $16 times T plus $10 times C. Okay? This is going to be our objective function. Now we need to determine if the values of each decision variables are limited by any restrictions. Okay? That is called the constructing the constraints, right? So in our case, each table uses 2 large bricks and 2 small bricks. And each chair uses 1 large bricks and 2 small bricks, right? So, and you are limited by the availability of the materials, which means you have only 6 large bricks and 8 small bricks, right? So we have constraints like this. First constraint would be for, let's say, for large bricks, two times T plus C is less than or equal to 6, right? And for small bricks, it's going to be 2T plus 2C less than or equals to 8, okay? And of course, both decision variable, T is greater than or equal to 0, and C is greater than or equal to 0, okay? So this is the complete mass formulation for the second example problem, which includes the objective function and the constraint set, including the non-negativity restriction, okay? It's pretty simple, right? So we've just talked about the window glass problem and the chair and table problems. And both of these problems are categorized into the product mix problem, okay? So generally, in product mix problem, there are n different products that could be produced, and each of these products consumes certain quantity of m different resources, okay? And every unit of a product I uses a sub ij units of resource j. And given the profits of each unit item, number I, and maximum amount of resources j, our goal is to maximize the profit, okay? And of course, many business resource allocation problems take this kind of form, okay? Product mix problem forms. And the decision variables, in this case, represents the amount of items produced. And using these decision variables, objective function and constraints have the following forms, okay? Of course, the objective function is the maximizing the profit, and we have, I could say, two sets of these constraints. The first one is resource availability constraints, and second one is non-negativity restrictions, okay? And the standard form of linear programming problem with maximized problem would look like this, okay? And in this case, the number of variables is n, and the number of constraints is m plus n, right? And actually, we can use some notations to write linear programs compactly, okay? So we can write C1, X1, C2, X2, C3, X3, to Cn, Xn as sum over I equals 1 to n, C sub I times X sub I, right? That would be the compact form, compact notation. Also, we can write each constraint here, A sub J1, X1, plus A sub J2, X2, and so on, A sub Jn, Xn, which is less than or equals B sub J, as sum over I equals 1 to n, A sub Ji times Xi, which is less than or equals B sub J. for j equals 1 to m, for example, okay? And of course, the non-negativity restriction, in this case, x1 is greater than equals 0, x2 is greater than equals 0, and so on, would be x of I is greater than equals 0 for all I equal to 1 to n, right? This is just straightforward, right? Okay, now then let's consider another example of LP modeling, okay? So in this example, a television company has to make a decision that how many 27-inch TV and 20-inch TV sets they need to produce. Okay? The market research indicates that at most 40 of the 27-inch sets and 10 of the 20-inch set can be sold per month. And only 500 working hours are available per month. And a 27-inch set requires 20 work hours, and 20-inch set requires 10 work hours, okay? And each 27-inch set sold produces a profit of $120, and each 20-inch set produces a profit of $80. And we assume that a wholesaler has agreed to purchase all the television sets produced if the numbers do not exceed the maximum indicated by the market research. So in this case, how many decision variables do we need? Yeah, intuitively, just two, right? One for the number of 27-inch TV sets to be produced per week, per month, and another for number of 20-inch TV to be produced per month, right? So we have two decision variables. Let's say x1 is the number of 27-inch TV sets to be produced, and x2 is the number of 20-inch TV sets produced per month, okay? And also, our objective function is the maximize the total profit per month, right? Objective function would be maximize the total profit. Okay? So using the given information, our objective function would be max $120 times x1 plus $80 times x2. And we could set equal to z, okay? And the resource constraints is going to be the number of 27-inch sets sold per month would be less than equals 40, right? Which means x1 should be less than equals 40. Likewise, another resource constraint would be the number of 20-inch sets sold per month would be less than equals 10, which is x2 is less than equals 10, right? And another constraint that we need to consider is about the working hours availability, right? It's going to be 20 times x1 plus 10 times x2. It's less than equals 500 working hours, right? And lastly, the non-negativity constraints on TV sets produced, which is x1 is greater than equals 0, and x2 is greater than equals 0. So this is the complete LP model for this problem. Okay, that's pretty easy, right? Okay, then let's take another example. This example, the Martin raises pigs for supplementary income. And he is trying to decide what to feed his pigs. And he is considering using a combination of pig feeds available from local suppliers. And he wants to save his money, so he'd like to feed the pig at minimum cost. Okay? But at the same time, he wants to keep the balance of some nutrition factors, such as calories and vitamins. Okay? And the cost, calorie contents, and vitamin contents of each feed are given in the following table. Okay? Okay, here. And we just suppose he's learned that each pig requires at least 8,000 calories per day and at least 700 units of vitamins. The further constraint is that no more than 1/3 of the diet by weight can consist of feed type A, because it contains an ingredient which is toxic if consumed too large a quantity. Okay. Okay. So again, first of all, we need to define the decision variable, right? So how many decision variables do we need? Again, 2, right? So let's say A represents the quantity of feed type A, okay? And B is the quantity of feed type B, okay? Based on this, we may construct the objective function and the constraints, okay? And what is our objective function? Yeah, minimize the total cost, right? So we want to minimize the total daily cost of the feed per pig, right? So our objective function is minimize the unit cost, let's say 0.4 times A, right? Plus 0.8 times B, right? And the constraints on the minimum daily requirements of calories and vitamins are required, right? So first, a calorie requirement, let's say calories requirement. would be 800 times A plus 1000 times B. Should be greater than equals 8,000. Is that right? What about the vital mean requirement? It's going to be 140 times A plus 70 times B is greater than equals 700, right? Also, we need to avoid using too much of feed type A because of the toxic ingredient in it, right? So how do you express the toxic constraints? It does say that no more than 1/3 of the diet can consist of feed type A, right? And how would you express this using mathematical expression? Okay, what about this? Let's name it toxic constraints, okay? So the A should be less than equal to what? 1/3 of what? A plus B, right? Does this make sense? So this expression exactly tells that no more than 1/3 of the diet can consist of the feed type A in it, right? And of course, lastly, we do need the non-negativity constraints, right? Which is A is greater than equals 0, and B is greater than equal to 0. So this is the complete math formulation for our problem, right? Which does include objective function and constraints, including the non-negativity restriction. Okay? Isn't it easy? Okay. Okay, now we will talk about some basic concepts associated with a linear programming problem. Okay? Like it says, a set of point S is a convex set. If the line segment joining any pair of points in S is wholly contained in S. Okay? So let's assume that S represents the shaded area in this picture, in these figures. Okay? Then which one is convex? Both? Which one is convex? Second one? What about the first one? Actually, in this case, each line segment joining 2 points in S contains only points in S, right? So for these figures, the S is convex, right? So both of them is convex in this case. Then what about this? Is this convex? No, right? Because in this figure, if you can see here, point A and B are in S. But there are points on the line segments AB. that are not contained in S, right? So this is not convex. What about this? The same reason, this is not convex, right? And what about this? This line is not convex, right? Likewise. And for any convex set S, a point P in S is an extreme point if each line segment that lies completely in S and contains the point P has P as an endpoint of the line segments. And let me ask you, which of these 3 points is an extreme point? A, B, or C? Again, let's just assume that S represents the shaded area in this circle. Then in this figure, each point ABC on the circumference of the circle is an extreme point of S. This is because this figure, A, the point A lies on the line segments AB and AC. And both AB and AC lies completely in S, right? And A is an endpoint of the line segments AB and AC. And likewise, here the point B lies on the line segments BC and BA, and both BC and BA lies completely in S. And B is an endpoint of the line segments BC and BA, right? So all 3 points A, B, and C are the extreme points. Okay, then what about this? Which of these 6 points are the extreme points? All of them is the extreme points? Okay, in this figure, points A, B, C, D, and E are extreme points of S. Although point F is on the boundary of S in this figure, F is not an extreme point of S. This is because F lies on the line segments AE, right? And AE lies completely in S, but F is not an endpoint of the line segments AE. That's why F is not an extreme point, okay? Now you can see which one is extreme point and which one is not, right? Excuse me. And the extreme points are sometimes called the corner point, because if the set S is a polygon like this, then the extreme point of S will be the vertices or the corners of this polygon, right? And the feasible reason for any LP will be a convex set. And the feasible reason for any LP has only a finite number of extreme points. Also, the optimal solution is an extreme point of the feasible reason, okay? So any LP that has an optimal solution has an extreme point that is optimal, okay? That is an important concept. I said any LP that has an optimal solution has an extreme point that is an optimal, okay? Okay, then in our everyday life, the term solution means the final answer to a problem, right? But in LP, any specification of values for the decision variables is called a solution. And a feasible solution is a solution for which all the constraints are satisfied. And the infeasible solution is a solution for which at least one constraint is violated. Okay? The feasible region is the collection of all the feasible solutions. So the feasible region for an LP is the set of all the points satisfying all the LP's constraints and all the LP's sign restriction. Okay? And then optimal solution is a feasible solution that has the most favorable values of the optimal objective function. I just read this. So if there is no other feasible solution with objective function value better than that, then the optimal solution is the feasible solution, right? In that case. So in this case, the most favorable value is the largest value. If the objective function is to be maximized, whereas it will be the smallest value if the objective function is to be minimized, right? And the optimal value of a function is the objective value of an optimal solution to the problem. Then let's consider an LP example like this. So in this case, x1 equals 2/3, which came from the second constraint. And if you plug in that value to the first constraint, then you would get x2 would be 7/15. So both of decision variable values, x1 equals 2/3 and x2 equals 7/15 is a feasible solution to this LP model. And in fact, it is the only solution to the problem, right? So it is also the optimal solution to the problem as well, okay? And what about this? Let's reconsider the window glass example. Here, the x1 equals 0 and x2 equals 0 is a feasible solution with z equals 0. The optimal objective, the objective function would be 0 for that, right? Because if you plug in that value, x1 equals 0 and x2 equals 0 to all of the constraints, then it will satisfy, right? It doesn't violate any of the constraints with x1 equals 0 and x2 equals 0. So that would be a feasible solution. But we don't think it's an optimal solution, right? For example, with x1 equals 0 and x2 equals 4, you obtain another feasible solution, which has larger value of z equals 20 in this case. That is much better than the z equals 0, right? Because our objective function would be maximize the total profit in this case. However, we are not sure whether this is the optimal solution, okay? So you could answer this question easily through the graphical procedure, graphical method. Because in this case, we have only two decision variables. And I said earlier in this class, the LP model with only two decision variables can be solved by graphical method so easily. So I think you will learn about it next time, okay? Mm-hmm. We have I think I cannot finish up the graphical method if I start right now. So I'm going to stop here for today, and next time, like I said, you will learn about how to use the graphical procedure for solving LPs for the case of only 2 decision variables for LP. Okay? Okay, then I will see you next time. Thank you very much. Bye-bye.